So why do we plot the magnitude in the log scale? Well, think about it. A transfer function, let's take a transfer function, g of s, is made up of different components, like, let's say, s plus 1 divided by s plus 2 times s plus 3 or something. That is different. You might have different components like these. Now, each of these are actually a complex number, isn't it? So you can write this as, for example, s plus 1. Take s plus 1. S plus 1, if you replace it by s equals j omega, you will get j omega plus 1, okay? And j omega plus 1 is, this much is j omega. This is 1. So it is a complex number like this, okay? 1 over s plus 2 is like that, or 1 over s plus 2, let's say. Again, by s equals j omega, you have 1 over j omega plus 2. You multiply it by its conjugate, etc. Again, you get another complex number, something like this, I suppose. It will have a negative part. So this will be, again, a complex number. Again, 1 over s plus 3 will be a complex number like that one or something. So each of these are complex numbers, okay? So we are actually multiplying them as complex numbers. So you can write, like, if you write it as complex numbers, you can write it as z1 over, let's say, z2, z3, or something like this. Each of them is a complex number, right? Or I should say not g of s, but rather g of j omega here. That's a better way. Each of them is a complex number of frequency. Now, if I can write this as in polar form as, let's say, r1 e to the j theta 1, r2 e to the j theta 2 times r3 e to the j theta 3. Or I can write this as r1 divided by r2, r3, right? This is r, e to the j, let's say, theta 1 minus theta 2 minus theta 3, okay? So e to the j terms have that nice property of being additive. Let me erase this and write it clearly. R is the magnitude of each of these terms. Now we have the multiplication. So we see that g of j omega, the magnitude of it is, let's say, r1 divided by r2, r3, let's say, right? And the phases, phase of omega for this thing is theta 1 minus theta 2 minus theta 3. So individual things are added up in the phase, and the individual things are multiplied or divided in the magnitude. Now, the good thing about logarithm, as you remember, logarithm of a multiplication is log x plus log y. Actually, the reason logarithms were devised in the past was to make multiplication easier. You convert multiplication, log, let's say, converts multiplication to addition, okay? You take the log, you add them up, and then you take the inverse log to find a complex multiplication. Now, this is exactly what we will do. If you take the logarithm, it doesn't matter. You can take it in the log 10 base, or any base is okay, ln is okay, but we usually use the log 10, 10 base logarithm of g of j omega. For example, in our case, this will be log r1 plus, not plus, minus, because you are dividing, log r2 minus log r3. So we can add up individual, if you use logarithmic scale, you can add up individual components of the transfer function, and that's a big advantage. That helps you, get, let's say, well, write it easier. Also, if you take the logarithm of not the magnitude, but the transfer function itself, okay, sorry, this is the logarithm of, let's say, some amplitude times the angle, and the logarithm gives, I have trouble in writing, I don't know why. Log. Log. E. So if you take the logarithm, you just get the real part, and imagine the real part of it gives you the logarithm of the amplitude, okay? So the Bode plot shows real and imaginary parts of the log of g of j omega. So I can maybe write this if I can. Since I cannot, that's the problem. For the plot shows the okay. There is another thing which is quite useful, and it is standard now. So we will be using that, and that is the measuring the transfer function magnitude in terms of the decibels. Decibels, probably you have here heard it in terms of the sound measurement, like for example, 90 decibels or 100 decibels is a very loud sound. This is also used in different applications. G of, let's say, j omega magnitude. If you want to measure it in decibels, this is taken as 20 times the logarithm 10 base 10 of, let's say, g of j omega. So the unit of this thing is decibels. Decibels. The bell comes from this Alexander Graham Bell, who devised the telephone. It's a unit, but it was a larger. It was a unit that it was not very practical. So there is a reason they multiplied it by 20. Now this is standard, so we have to accept it as it is. So we usually measure the magnitude of the transfer function in terms of decibels. That is, you take the logarithm of the transfer function and multiply it by 20. If you take the logarithm of the transfer function and multiply by 20, you don't have the plot of the plot will be the plot of magnitude. Magnitude will be decibels versus, let's say, log of omega, and the plot of the phase will be phase versus log of omega. So in effect, this will be a log-log plot, and this will be a semi-log plot. Okay. Now, the Bode plots is a nice and simple graphical way of showing the frequency response of a system. The main advantage as I have told you, is to if you have a transfer function made up of many small transfer functions, that is, systems this is very frustrating, actually. Why? Systems in series are simple to add. If you take the logarithm, you can simply add them. And you can also show low and high frequencies in the same plot. Because we are using logarithms. That's a big advantage also. If I were able to write it. Okay. High, let's say, and low. They can be shown in the same plot. So we can go on and try to plot them. By the way, it is quite easy to plot these things on MATLAB or any kind of software. You just say something like Bode of the transfer function and then get the plot, or Bode of G omega if you want to give the omega axis by yourself. The thing is, you have to know how to interpret these things, even if you plot them by a software. Okay. So we have to try to interpret these things. Now, the transfer function of a system, a general transfer function, let's say, function, is something like this. G of s is some, let's say, k times. You might have zeros, s plus, let's say, z1, s plus, z2, etc. And then you have poles. Okay? Zeros and poles, some of these might be missing. Then you might have no zeros, etc. But it doesn't matter. Now, this is not the transfer function we will be using in the border plots. For border plots, we have to convert this to something else. It is related, not too difficult to convert, but we will be using it the following. K times, let's say j omega. By the way, we shouldn't be saying g of s because we will be using j omega here. We will be using the so-called time constant form because it makes things much easier for us. We will see why. Okay, we will convert our system to time constant form. If you have a system that is in this form, you have to convert to, well, first of all, you should replace s by j omega. Then you should be finding the so-called time constant form. So let me just give you the example. Let's say g of s equals s plus 1 over s plus 2 times, let's say, s plus 3. Okay, a simple example. We don't use it in this form because this is not what we want. We rather have to put everything in the following form. S plus 1 is okay because this last term is 1, but these ones we will do 1 over 2 times, let's say, 2s plus 1, okay? This thing has to be written like that, times 1 over 3 times 3s plus 1, okay? So 1 over 2 times 1 over 3 is 6, and this 6 goes upwards, so this 6 times s plus 1 over 2s plus 1 and 3s plus 1. Okay. So we are in the time constant form now. We have to replace this by j omega. G of j omega is going to be 6 times j omega plus 1 to j omega plus 1, 3j omega plus 1. So this is the form we should convert our transfer function to. If you do that, then your system is going to be, well, you can analyze the individual terms, find the individual border plots, and then add them. As you will see, adding them is quite easy if you know how to do this. Now, we will be For example, let me give you an example again. Let's say that our example is like g of j omega equals some gain k and j omega t1 plus 1 divided by, well, you can have three s terms as you might remember. So you might have j omega squared okay. Now we will take the logarithm of this, or we will express this thing in decibels. For example, the gain expressed in decibels of this system would be 20 times the logarithm of g, and that will be the individual terms 20 log k plus minus 20 log, let's say, okay, something like this. This is the gain part. And for the phase part, which is the angle of g of k, is going to be the angle of k plus the angle of j omega minus the angle of j omega squared minus the angle of omega ta plus 1. Each of these terms, the gains and the phases angles can be rather easily computed, okay? And we will see that, well, you can kind of easily find each of these terms. They don't look very easy now, but once you get used to it, you can sort of easily put them down. And once you easily put them down, you can plot the individual transfer functions, individual terms like these. Let me say, this is one individual term, this is another, this is another, this is another, and these are individual terms as you see. If you plot each of these and add or subtract them, you get the total transfer function. So we can say the following: all, I should say frequency response, all transfer functions, I should say the correct expression is the frequency response here. But have the following terms. You have, they all have a gain term. There might be a free gain term, okay. Then you might have j omega to the power n. N can be like 1, 2, or let's say -1, -2, -3, or whatever. Then you might have j omega t plus 1, t being the time constant. Usually you have plus or minus 1 here, which means you either have j omega t plus 1 in the numerator, or you might have 1 over j omega t plus 1, which is in the denominator. Okay. This is another term. And you might have a second order term, which we will be showing by, let me just show it like this. Usually it will be a minus 1, but you might have this. Where does this come from? This comes from the following: 1 over s squared plus 2 zeta omega n s plus omega n squared. Or I should say, in the numerator, let's have omega n squared as well. Okay. Divide everything by omega n squared. So you get 1 over s over omega n squared plus 2 zeta omega n goes, we are dividing to omega n squared, so that omega n goes away. S over omega n, right, plus 1. Now replace it by j omega. Okay. S equals j omega. If you put that, you are going to get 1 over, actually j omega squared is minus omega, but let's keep it for the time being. This is what we have here, as you see, in terms of the minus 1 quantity. So you might have a quadratic term like this, which we will be analyzing. And finally, I'll just mention that you might have something, a term like this. This is time delay term. In some systems, you have time delays, so that the time delay, especially in chemical processes, time delays show up in the transfer function, like e to the minus sd terms like this. We don't usually encounter them in mechanical engineering, but in chemical processes, it's quite possible that you have time delays. So in some transfer functions, in some frequency responses, you might have time delays. So typically, we have all these terms, 1, 2, 3, 4, and possibly the fifth one. If you analyze and learn how these things are the Bode plotted, then you can easily plot the Bode plots. Okay, or at least plot the Bode plots of a system with these components. Okay, or alternatively, you might understand how these are plotted. Okay, it is not too difficult to understand. Now, let's start with
Hocam, I'm sorry to interrupt you. May I ask something from the
Sure.
example we solved before you write those things?
Okay. Which example?
Yeah, this one.
Okay. Okay.
Hocam, while we calculating the phase angles, why we subtract the denominator? Like, isn't it a whole, like, while we drawing it and real and imaginary,
Mm-hmm.
we use both of the parts. So, like, why do we separate them and write it as minus?
Okay. Maybe I passed that part rather quickly. This example, if you remember,
Hmm.
for example, I have given this example, right? SO plus 1, S plus 2, S plus 3.
Mm-hmm.
You can write each of these terms as individual components with individual angles. So you have e to the j theta 1 divided by e to the j theta 2 and then e to the j theta 3. This e to the terms can be combined to be the numerator terms minus the denominator terms. That's
Okay,
why
hocam.
we subtract them. Do you see?
Mm-hmm. Mm-hmm. Okay.
That's the reason. So the phase angle is simply the numerator phases minus the minus the denominator phases.
Mm-hmm. Okay, hocam.
These steps I have to go maybe a little bit slowly. If I go, through them fast, I might lose you. But each of
Hocam,
them,
uh, I'm sorry. I'm so
yeah.
sorry. Say,
Oh, no, it's okay.
do we need to separate k? I thought it was like a coefficient or something like this. A constant
No,
number.
it is a constant number, yes, but it shows up, as we will see, in the border plot. It affects the border plot. Okay? K is
Mm-hmm.
the gain of the transfer function.
Okay. Thank you, hocam.
Mhm. Plotting, let's say, each term. So we will start from the K term. So let's say log K or 20 log K. We take the decibel. Let's say, let me just say it like this. Let's say G1 is K, the first component of G. So the G1 in decibels will be 20 times log of K, which is a constant number. Um, the phase of this G1, it will be just 0 degrees, okay? It won't have any phase. No phase contribution, okay? So, if you plot it, if this is omega, and if this is, let's say, the magnitude in dBs, I should say, not just say dB here, you get a straight line as 20 log K. And if you plot the phase, pi versus omega, by the way, these omega things are logarithmic, but it doesn't matter. You just have, if this is 0 degrees, this is 0. Okay. This is what we get. It is trivial, but this is what we get. Okay, this is the first one. The second one, G2 is, what did we say? j omega to the power n. Okay. So the G2 in dBs is 20 logarithm of, let's say, j omega to the power n, which is 20 n times log of j omega. What about the phase? Or I should say phi 2 of omega is the phase of G2. And n times 90 is why. Now think about it. We are talking about j omega. This is the real axis. This is the imaginary axis. Okay. What is j omega? J omega is something like this when n is equal to 1. This is j omega, right? What is j omega squared? J omega squared is j squared times omega squared. It's simply minus omega squared, isn't it? So it is something like this. So this is j omega squared. And j omega cubed is something downward. And j omega to the fourth is in this direction. And for example, 1 over j omega to the minus 1 is 1 over j omega, or it is minus j over omega, right? So you can say that this is, this is minus 1. As you see, the phase angles are, for j omega, the phase angle is 90 degrees. For j omega squared, it is 180 degrees, right? And for j omega to the minus 1, it is minus 90 degrees. Okay? So this is how we find this thing, n times 90 degrees. Okay? And we will see the gain is this, by the way. You can write this as 20n log omega. Log of j is simply 1.
Hocam, why the J term is gone?
And log of j omega is simply log omega, that's why. It is Log J is 1, that's why, I think.
Oh, okay. Okay, hocam.
So, let me finish this and then I'll take a break. Phase is 90 degrees. The gain, if I plot the gain, in terms of dBs, let's say, and this is omega. If I look at it, 20m log omega, okay? You have, when omega is 1, you are at 0 dB. Because when omega is 1, you have log omega, which is 0. So this is where you are, 0 dBs, okay? Now your slope is 20 times n. N can be like, if n is 1, you have something like this. If n is -1, you have this. Sorry, n is -1. You have a curve with a slope of -1. So the slope here is 20n actually. Here also, the slope is 20n. Which means that, for example, if you go from 1 to, let's say, 10 in omega, here you are going to get to -20 dBs, or here you are going to get to 20 dBs. And furthermore, if you are in, if n is equal to 2, you have a slope of again 20n, which will be, you will get to 40 dBs in one so-called decade. Okay. And here you might have, let me plot this as well. So let me very briefly plot the phase. The phase. Let's say that it is, you start from 0, -90, -180, etc. For example, when n is equal to etc. Okay, the phases are not 0, but they are constants for each term. Okay, we are getting late, so let me stop at this point and take a break.